Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we're going to finish up my discussion with flat earther Brandon Toy about the black swan image. Now, in our first episode, we went over the image with a fine-tooth comb, including not only the black swan image, but the construction documents for the oil platform and up-close images of the same platform. And we came to the conclusion that we could not identify any parts of that oil platform below about 15 to 20 feet above the water level. Now, in this episode, we're going to discuss possible reasons for that. Brandon has his ideas. I, of course, believe that it's Earth curved. So let's cue up the music and have a listen to the discussion. I want you and I to sit down and just make an honest assessment of what we can and can't see. And I think that we're agreeing that the bottom 15 to 20 feet of that platform we can't see. Fair enough?
We can't make anything out.
Yeah. We cannot identify anything. We can't identify any structure.
We can't identify the lower part of that structure is too distorted to identify anything. Yeah.
Okay, good. Now, I have a pretty good idea of why that's happening, but
really,
it's my understanding that you have your own ideas on what that's happening, and one of them has to do with compression. Is that correct?
Compression is a possibility, yeah.
Well, why do you think we can't see the bottom 15 or 20 feet of that? You know, what's your explanation for that?
It could be there's the water's choppier than the picture. It's further. It's just too distorted. Could be compressed. It's just too far to make any distinct identification of anything.
Okay.
Within that jumbled mess at the bottom there. That's what I would say.
But we do have a different picture with Hilltop or Hill House, though, right? I keep calling it Hilltop.
Yeah, Hill House is a lot clearer. Yeah.
Yep, and it's about 2/3 the distance. Would you agree?
6 divided by 10. Yeah.
Yeah. All right. Now, that additional 3 miles. 3.2 miles, in fact, out to habitat.
Mm-hmm.
You think that these conditions, the compression, the water, the wave size, the basic distortion, you think that 3 miles will account for the differences between those two photographs?
Yeah, sure.
Okay. And would you be able to quantify that in any way?
Probably not.
Okay. Well,
how would you start to quantify that?
Well, I could look at refraction. I could look at a number of things. I could try and measure some stuff. But I do have some questions that are rather bothering me, shall we say.
Okay.
This right here, that right there, and these are the cross beams, right?
Yep.
Okay. We can make them out.
Yep. For the most part, yeah.
Okay.
We can see that there's some cross beams there.
All right. Well, let's say those cross beams are 2 feet wide. Okay. Why can't I make out a 2 foot wide cross beam here, but I can't see 15 feet of structure? Just a couple, a yard away.
Yeah, you're getting closer to the surface, first of all.
Okay, so you
So
think
the closer to the surface you get, it appears on this image, the more distorted it is.
okay.
And that's
Is
typically true of the closer you get to the ground, the further you look out, the more distorted it is, right?
okay, right here we have a leg of the platform, and we see the width of the leg here, and we see the width of the leg up here. Are they significantly different? How about this one over here? Or that one?
Yeah, that they're all distorted. Yeah.
Are they equally distorted from top to bottom? Or are they pretty much okay at the top and then wildly distorted at the bottom? Or are they about the same width all the way down?
Oh, they're pretty distorted. I don't see too much of a pattern.
Yeah, but I mean, is that just as wide there as it is down here?
No.
It's not.
No, it looks like it's pretty distorted up at the top. And
you mean this part right here?
At the bottom.
That's part of the mount. How about that one right there?
Yeah, that looks pretty distorted at the bottom, yeah. I mean, it looks pretty wider at the bottom.
Could you measure the width of the bottom?
No, I don't think you could. I think that'd be a waste of time to try to measure that.
Could you measure the width at the top?
Again, I mean,
I'm going to go ahead and...
purpose?
Well, to check to see if it's distorted.
Look at how distorted this thing. Just look at the overall image.
Yeah.
It's...
But here's a question, though. Look right here. These are all pretty straight, aren't they? Isn't there like a particular level up here that all of a sudden this distortion really kicks in? That's a pretty straight deck, isn't it?
You've just got long lines coming off of the object, and you're seeing more distortion at that point. I think the whole thing is distorted.
Well, you think it's distorted down here the same as it's distorted over here?
I don't know. It's a different kind of structure over there. I think the whole image is distorted. Just stand back and look at it.
Yeah, but that's a big S right there. These are kind of straight. Those look pretty straight to me. As a matter of fact, you can actually make out where that cross is.
You can tell that it's something that goes from the top to the bottom, but...
How about that deck right there?
You can't make out any detail on that.
Yeah, but this deck, is that relatively straight? And can you see a nice straight edge right there? Kind of the same thing right here.
That particular part right there seems less distorted, yeah.
How about over here? Is that kind of straight there? How about that one?
That's... Bob, can you agree that this is a distorted image of an oil rig?
Oh, yeah, very much. Okay. But I'm looking at the bottom of it right now, and I'm trying to see if the level of distortion that we see here is present down here, and I don't think that it is.
How are you quantifying that, the level of distortion?
Well, you see how much this is twisted here? And all of these are twisted? But look at these nice right angles right here.
Yeah, like I said, it's a different kind of structure. So you've got something that's sticking out maybe 50 feet. You've got air turbulence.
Okay.
Yeah, that's going to look a lot.
I think there's a lot more distortion up here than there is down here. I think the whole image has got some blurriness and distortion in it, but I think the distortion's worse up here than it is down here. Do you think that's fair?
Okay. If you want to say that.
What would you say?
I would say the whole image is distorted.
Equally. Okay.
I'm not saying equally. No, I'm not saying equally. I wouldn't know how to quantify which part is more distorted than another part. And I wouldn't try.
Okay, that's fair enough. So there's Hill House.
Yep.
There's a little distortion right here. You see that's a little bowed. But overall, that doesn't look too bad, does it?
No, down in this part. Clearer.
Yeah, it's a lot clearer, and you see nice straight lines here. And you clearly see structure below that walkway 15 feet above the water.
Yes, that one is a lot clearer. Correct.
Okay. Well, then let me ask you the obvious question. If you think, if it's your thought that this is distortion down here and that's the reason that we can't see, or compression, would you be able to explain why it would match a curvature calculator at different distances? I mean, if things disappear from the bottom up because they have compression, why would that match a curvature calculator, a variety of distances from a variety of different observer heights? Do you think that
Well, I never said that it was missing, hidden from the bottom up because of compression.
Okay.
That's not a claim that I ever made.
Okay.
I said that compression could cause distortion at that distance.
You said water chop, distortion, and compression were possible reasons that 15 feet was missing.
Miraging. Miraging is another one that can hide objects from the bottom up at distance. Now, it matching a curvature calculator, I don't think it does.
Okay. But if it does, do you think, if we have a day that doesn't have distortion, and these views are extremely clear, and it does match the curvature calculation, would that be caused by distortion or miraging or compression or water chop as well?
This isn't matching the curvature calculation.
Well, it depends on how much refraction there is.
The picture. So
yeah,
you trying to use the curvature calculator on just this one piece of the photo kind of ignores the rest of it. The rest of the photo, though, doesn't it?
Well, how does the top part of that oil rig come into play in trying to figure out Earth curve?
Sorry, the top part?
Yeah, the top part, up here. Now, if I were to measure to the height of that mast right there, for example, on that crane, all right, I could probably do something by trying to find its angular size above the horizon, such as the mountains that Ranty did, and compare that to another known object to see whether or not they're higher. For example, with Ranty's image, the mountains should have, quite frankly, been higher than the Blackpool Tower in the front. That I could probably, I can measure that angular height. All right. And
that'd be a fool's errand at that distance. Yeah.
Yeah, I think it would be a fool's errand with this one. But can I measure refraction by looking at an image and knowing the distance to that object?
No.
Okay.
No, I don't think you can.
All right. Well, all right.
Do you think you can?
So with refraction, the way refraction works is that it curves light, and any curve has got a radius, correct?
It distorts light coming from distant objects.
Yeah, but refraction specifically is the bending of light, correct?
Yeah, I understand. I'm trying to keep away from describing the how and describing the what, but go ahead.
All right. Now, one of the things that you hear on the when you're looking at the Earth curve calculators, you have the radius of the Earth, and then you have this thing for refraction of 7/6R. You're familiar with that, right?
Yeah, that's that mechanism by which you make it impossible to falsify your model. Yeah, I'm familiar with it.
Okay. So you realize 7/6R is actually just the distance of the radius. I mean, I could have just given a number of miles.
R is radius, yes.
Yeah, but you don't. It's not dependent on another object's radius. It's just a distance. It's a way to estimate what that distance would be, but it's just the distance of the radius.
I don't have a problem necessarily with you using R, besides the fact that you're baking your model already into the calculation. If you're trying to use the calculation to prove that we live on a ball, it's kind of self-referential, but
okay,
whatever.
All right.
That wasn't what I took issue with anyway.
All right. Now, we've already kind of agreed that there's refraction present in this photograph, and that both platforms are photographed in the same image.
I would say there's always refraction. Yeah.
Yeah, but on this particular photo, we're saying that there is refraction, and since both oil rigs are in the same image, would you agree with the concept that the refraction would be similar for both of them, rather than, you have X amount of refraction on the right side of the picture and Y amount, which is significantly different on the left side? Would you say it's all pretty much uniform?
What do you mean by uniform?
Well, would you say that there's the same amount of refraction affecting our image of habitat as there is on Hill House? The same amount of refraction is present, however the distance is different. So effectively there will be, you won't get as much distortion at Hill House because it has less distance to undergo the same amount of refraction, because the atmosphere has a certain amount of refraction in this image. Would you agree that that's a fair statement?
No, I wouldn't make that assumption.
Do you think the refraction value, as far as the refraction index of the atmosphere, is different between Hill House and habitat?
I don't know.
Okay. Do you have any reason to believe that it would be? It's the same atmosphere and the same image at the same time under the same conditions.
Yeah, I guess I do have a reason.
Okay.
In that the temperature varies based on distance from the shore, or could be temporary temperature variations, could be wind variations. I don't know what's going on out there.
So are you kind of going down the line that you think that the temperature of the water, for example, between the shore and Hill House is different than the temperature of the water between Hill House and habitat?
I'm saying that there could be a difference between where habitat is and where Hill House is.
Okay.
But let's say I agree with you, and that it's the same refraction, and the only variable that changes in distance.
Okay.
What's your point?
I'm just curious if that's how you see it. I'm curious as to whether or not you think that's a reasonable assumption to make, because whenever we try and evaluate these things, we have to have kind of, we have certain things that we measure, and then we try and interpret those measurements and try and figure out what's going on. And sometimes when we do that interpretation, we make some assumptions. For example, I can assume safely that the composition, as far as oxygen and nitrogen of the air between the shore and Hill House, is the same as the composition of the air between Hill House and habitat, because it's the same atmosphere. So the composition of that air will be the same. I can assume that the humidity over that period of time is going to be roughly the same. It may not be exactly the same, but I don't know if it's going to change enough to actually have a difference in the outcome. And I can assume that the refraction index is roughly the same for both images, because it's going through the same conditions. Now, there may be minor variations in temperature. Say there's a cold current offshore that somehow dips between habitat and Hill House. There may be a little bit of a difference there, but I don't think we're going to see a difference in 30 degrees in the temperature of the sea or the air between those two locations. It may be a fraction of a degree, and that may actually have an effect. It's a question of whether or not that effect is significant. Would you agree?
Let's accept your assumptions and go ahead.
Okay. All right. Well, Brandon, thank you very much for stopping by and having a chat with me today. Is there anything? Yeah, that's it. Is there anything in particular you wanted to talk about? We can spend a few minutes talking about yours.
You got to the punchline, Bob. I think you're missing the punchline. What's the punchline?
I don't have a punchline. This is just you and I having a discussion. We were looking at a photograph. We were looking at photographs and seeing if we could find some common ground on them.
How much of that platform should be missing in the back?
Habitat?
Yeah.
With normal refraction?
Yeah, just a basic calculation.
45, 48 feet. And we're seeing at most 15 missing?
Yeah.
So we're seeing an extra 30 feet?
Okay. So you do acknowledge that we are seeing more than we should based on
normal refraction. You betcha. Yeah.
Yeah, and not to mention the fact that the apparent horizon is behind both platforms.
Yeah, not to mention it. Now, just out of curiosity, if we do see more than we should, what does that mean?
You know what this all comes down to for me? Because I wouldn't say, oh, it means the Earth is flat.
Well, I don't think you would. I think you're smarter than that.
No, we can't determine the shape of the Earth optically like this because we get contradictory information.
Okay,
there's too many variables and too many unknowns, especially for viewing objects at a distance.
Okay.
That I don't think we could draw a conclusion.
Well, we can. We definitely can. It's whether or not those conclusions are meaningful. We can definitely, for example, I can take that and I can calculate what the apparent radius of the Earth is. And then I can compare it to the radius of the Earth obtained by other means. And not only will that help me predict what I would see on that day for other things, it would also give me a direct measurement of how much refraction was present. And I derived that the other day, and that's not a big deal. But I think the take-home message on this is two things. First of all, seeing farther than we should does not mean the Earth is flat. It means it's still got a radius. It's just bigger than we thought it was, and it's still a sphere. It's just bigger than we thought it was. It by no means means that it's flat. Does it mean it's cylindrical or pear-shaped? Well, the only way that you could tell that would be consistently measure do measurements that help you determine what the local radius is based on your measurements in a variety of cardinal directions at many, many points on the surface of the Earth. If they all come out to the same radius, there's only one geometric shape that will do that, and that's a sphere. Is the Earth a sphere? No, it's not. It's off a little bit, but it's pretty damn close. And yeah.
What would be our baseline if we did all those measurements in different directions and then took some kind of average or?
Yeah, you could do an average of it. You could, statistically what you would do is say you got 10,000 measurements of the radius of the Earth.
I didn't get to my question.
Oh, go ahead.
What would be our baseline for refraction?
Well, we could measure refraction for one.
The method you just described to me of measuring refraction assumes that you're already on a sphere to determine the amount of refraction that there is.
That's not the only way to measure refraction. It's a handy way to do it when you're analyzing a photograph. It only has two terms in it. But there are many ways of measuring refraction. You can do it experimentally. you can
How do you
find
do it
refractive
experimentally?
indexes. Well, how did they find a refractive index to begin with? They took a piece of glass and they shined a light through it and saw how much the glass was bent, and then they compared that to other substances, and they learned how to calculate refractive indexes.
Bob. That's not applicable to these long distance observations through very dynamic environments.
Well, but the bottom line is, if you look at naval almanacs, which contain figures to aid you with navigation, you can actually see that refraction is included in those. There's a correction for refraction, and it's accurate. So their understanding of what's going on reflects reality.
Wait, naval almanac. So you're getting your refraction values from a naval almanac? How did they derive?
It's one way of doing it. It's one way of figuring out how much refraction is going on. But yeah.
How did they figure it out?
Experimentally.
In the lab, like we just discussed?
Experimentally and at sea, yeah. What they do is they take a known
baseline if they did it at sea, though.
Yeah, well, what they'll do is they'll take a known location, for example, and they'll use a sextant to try and determine what that location is on different days with different weather conditions. And they'll be able to sit down and say, okay, well, if the sun is X number of degrees above the horizon, standard refraction is this. It's 1 minute, it's 2 minutes. And
would you agree that you have to know what your baseline is in order for you to get a
your baseline is where you are
for refraction?
Your baseline's your known position.
If you're looking off at the distance, you're saying, I know where this place is.
Yeah.
And then you take your sextant and you measure, it's what is it called? Elevation, declination, whatever. You measure it.
Well, what you do with sextant,
value to?
Yeah, what you do with the sextant is generally what's called a 3-star fix. And that will
I understand how to use a sextant. I've got one, but my point is,
Uh-huh.
What do you use as your baseline?
Your
what
known
it should
position.
Look like?
Your known position. And then the refraction has to do with where the star is above the horizon, for example. So if it's at the zenith.
How high above the horizon should it be, though, Bob? That's the question.
Well, you know where the stars are. We have something like 57 known navigation stars that are very precisely plotted. And what you do, for example, is you can plot the position of a star at zenith where there's no refraction at all, and then you can compare it to the position of the same star at the horizon in the same night and see the difference. So
you know that they don't even rely on any star measurements under 15 degrees.
Correct.
So
and why is that?
Because of refraction.
Exactly. We never make observations within 15 or 20 degrees of the horizon. It's too refracted.
Right. So
and we
you
can measure
haven't
that.
answered my question on what the baseline would be. If I'm measuring a star, and let's say I say 10 degrees above the horizon right now.
Mm-hmm.
How do I know that it should be 10 degrees above the horizon? Say another day it's 12. Let's say another day it's 8. What is its true position?
Okay, its true position is based on what you observed its position at zenith. Its true position is based on that. And then what you do is you monitor it as it comes down towards the horizon and see the difference in the change. There's a thing called the King rate, which is used with an equatorial mount telescope. And that takes into account the fact that objects tend to elevate or loom as they get down towards the horizon. So it's a way to be able to actually follow a star as it gets closer to the horizon. But, when you start getting down within 10 or 15 degrees of the horizon, your readings kind of get squirrely, and that's why they don't recommend it. If you're doing a navigation, if you're doing a sextant reading, you want to be able, my vision of it is that you want to have it accurate enough that when it says that you're at the entrance to the port, you can see the entrance to the port. It may be a mile away, it may be 2 miles away, but you can see it. When you're doing a more formal one, say a land-based sextant reading, you know, there's a lot of other ways that you can do it. Now, there was a very interesting documentary that came out when I was in school, and that was how did they determine the exact location of the border of the United States at Natchez, Mississippi. And it really was a fascinating study of how they did it. And it was multiple readings. And, you know, the easiest part was trying to find the latitude. The toughest part was trying to find the longitude. Any idea how they did it? Before they had accurate clocks?
How'd they do it?
They had an almanac. And what they did was they plotted the moons of Io, or of Jupiter, specifically Io. And they noted the time that it would be occulted by the planet. Very precisely. They noted the time that it would be at Greenwich, England. So what they did was they found local solar noon at Natchez, and then they observed Jupiter and Io, and when it occulted, and it does it, you know, it does it at least once or twice a day. What they did was they measured the occultation of Io and compared that to local noon versus what time it would have been at Greenwich, England, and they were able to find the longitude that way. It's a fascinating thing. We have better ways of doing it, of course, now, but you know, this is back in the late 18th, early 19th century, and you know, their tools were a little limited back then. It was just a fascinating thing if you're ever interested in geography or anything, you know, where they came up with latitude and longitude. Well, Brandon, it's 4th of July.
It's just a cause and effect relationship, essentially, right? I moved this far. These stars move this far. And once you understand those relationships between position and where the stars are, it's a predictable pattern.
To some extent, yeah.
Yeah.
Yeah. All right. Well, Brandon, thank you very much for stopping by. I don't want to take, I know your time's valuable, and I've got things to do with my family too on this holiday. But thank you for stopping by. I will send you a full copy of this uninterrupted recording. We've been about an hour and 4 minutes, 4 minutes, 20 seconds right now. So I'm going to go ahead and stop the recording. Well, folks, thank you very much for joining Brandon and I appreciate Brandon joining me on my channel to have this discussion. I think it went very well, and it was an enjoyable chat on a 4th of July. Now, it's rather apparent that 15 to 20 feet of that oil platform is not visible in the Black Swan picture. Now, I've gotten some notes from the original author of the Black Swan video, and it's his opinion that there is no hidden part of that oil platform. It's all compressed. Well, quite frankly, that's silly. And we all know why. We watched the entire discussion and the analysis of the photograph. Apparently, the author of this picture never really looked at it. Second of all, the question of compression, I don't think is a tenable answer to why a portion of this platform is missing from the bottom. And I'm going to go over this on Thursday, where I take apart some of these arguments and I bring up the points that were made during this interview. Brandon seemed rather surprised that I didn't have a gotcha for this. And I really didn't, but that's not entirely true. What I wanted to do is I wanted to have this discussion with Brandon and let him talk and give his reasons for why he feels the way he feels. And during the course of that discussion, there were some very significant things said by Mr. Toy that will come into play with many of the flat earth arguments. And we're going to go over those on Thursday. I'm also going to address this issue of compression on Thursday. And we'll see whether or not that's a viable alternative explanation to Earth curve. So until then, this is Bob the Science Guy signing out from Northern Michigan. Make sure you hit that like and subscribe. Now tomorrow, on Wednesday, I have a 4-hour telescope session condensed down to 30 minutes, basically going from object to object. So it should move pretty quickly. And I hope that you'll have a chance to look into it and enjoy it. Take care, folks.
Mama, please make them hear me, or I can't teach them anymore. feels too deep for me. Feel my brain getting real sore. Above the science guy. Above the science guy.